All right, let's start, everyone. Hello. 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 I was working with some students during my office hour, and I forgot to take my classes with me, so it's all blurry. Yeah, okay, so please guide me in case I don't see you. So this is the daily lecture summary as usual. I have made it even more convenient for you by putting in the sections that are directly related to the practice problems. Let me explain a little about the practice problem. So you have the big picture. Okay, so as you know, there are 2 exams. Okay, down here, yeah. All right. Let me not zoom in here. So you have the big picture. In exam 2.1, I listed problem 1 and problem 2. Okay, so both of them are in exam 2.1 in the previous semester. But if you look at exam 2.2, maybe let me zoom in the other window so you see. In exam 2.2 down here, I listed 3 problems. Problem 1, 2, and 4 without problem 3. So that means that I already removed problem 3. But so what does it mean seeing both problem 1 and problem 2 in exam 2.2? What it means is as follows. In exam 2.1, you can expect that I would give one of those 2 problems. Okay, one of the 2 problems, meaning either problem 1 or problem 2. All right, and then suppose that I give problem 2, right, in exam 2.1. Then problem 1 and problem 4 would be part of exam 2.2. Right, so one of those 2 problems would be exam 2.2. Okay, does it make sense to everyone? So if there's questions, please ask me. So because I don't know yet which one I give, so that's why you see that in exam 2.2 I listed all 3, but eventually one would be eliminated just because of the one would be eliminated would be the one that I give in exam 2.1. Yes. Can you speak louder?
So that there are 4 problems between exam 2.1 and 2.2, right?
There are 3 problems. Problem 1, problem 2, and problem number 4. I essentially remove problem 3. Okay, so 1, 2, and 4. So in exam 2.1, that's either problem 1 or problem 2, and in exam 2.2, the remaining 2. So I gave an example. If I gave problem 2 in exam 2.1, then problem 1 and or problem 4 would be in exam 2.2. Okay? And that's all. Yeah, will not have problem. You don't have to. I mean, for those of you who are interested, you can do for self-learning, but will not be in the exam. Okay? So, I'd like to review problem 1. In a way, you just did it, or you already did it, and we'll turn in. That's basically problem 5.1, right? And 5.1, and I even shortened 5.1 and ask you to do exactly the question that is related to problem 1 in exam 2.1. Okay, so this is really have a lot of preparation ahead already, and so everyone should be on top of this. And in addition to that, I have the solution guide in the form of the best solution from last semester, and let me show to you one of those would be, I really suggest to look at Team 7 of fall 2014, and and so here's their work, and let's and question 2. See, let me zoom out so that I can navigate. I'm sorry, like for those of you who are late, I forgot to bring my glasses. I worked with students during my office hour. I took my glasses off, and so now I'm almost blind. But I can still read. Okay, so I think that's the exponential. Okay, the exponential function. Let me see here. Something. It's this one, but this one is between this is for the interval 0 to 1 or 0 to 2. Okay, yeah. So the part 5.1.2 is what you want to look at. 5.1.2 is from the interval from -1/2. Let's see, where is it? Let me zoom out a little here. You see, they need much more extensive work than I asked you to do this semester. Let's see, this is already 5.2. I already passed that point. Or this is 5.1.3. I think it's right somewhere here. Yeah, right here. Okay, so this is section 5.1.2. Everyone should be on top of this. You have complete solution, very detailed. And so let's look at the statement of the problem. In meeting 42, yeah, let me show you. In meeting 42, like I said here, I provided for you meeting 36 and meeting 42. In meeting 36, I discussed section 8C. So this is the beginning of projection. In section 8C, and that is on the interval from 0 to 1. But this is the beginning. Okay, you need to really be on top of this section. And I provided to you the solution guide for the projection in the case the interval is not from 0 to 1. And this is very important. This is the general method that is described in detail in this Google Doc. Okay. Now let me bring up. Let's see. Yeah. Let me bring up the problem statement. Okay. So you see this in this problem statement. You are given an exponential function and an interval from -2 to 4. And you know that from my notes, handwritten notes, okay, which is here in meeting 42, my handwritten notes is right here. Okay, so if you bring up my handwritten notes, I thought that I had it. This is section 8C. Let's see. Here. All right. So in this, and if you go down, you see that here is the beginning of my explanation. And I just noticed that there's a misprint. This should be really exam 2.1 problem 1. Okay. For some reason and what I explained up there was really problem 4. I mean, at the beginning of this handwritten notes. Okay, so what's the method? The method is you want to map whatever interval that you are given, and in this case from -2 to 4, okay, into a new variable called x bar, and x bar goes from 0 to 1. Okay, so I think this is probably the exact problem itself here. So that's why you see the interval is from -2 to 4. So essentially, when x is equal to, let's see, when x is equal to -2, this is the x-axis here. When x is equal to -2, you want x bar equal to 0, right? Because you want to map the interval from -2 to 4 to the interval from 0 to 1. So when x equal to -2, you want x bar to be equal to 0, okay? And when x equal to 4, you want x bar to be equal to 1, all right? So this whole interval here is mapped into 0 to 1, right? From -2 to 4 to 0, 1. Well, you know, the result is a straight line, and this is the equation, x bar equal to alpha plus beta x. So that, and this is the same again. When x is equal to -2, x bar is 0. So therefore, you have the first equation, right? And and when x equal to 4, x bar equal to 1, you have the second equation. Okay, so two equations, you can find the straight line, meaning that you can solve for alpha and beta. Okay, so I think yeah, that's what I wrote down here. So once you have x bar in terms of alpha and beta, is there anyone who wish me to show to you how to find alpha and beta? I can do that, but it just will take me more time. Right? So this is just finding a straight line. It's even some of us may have learned from middle school, even not or high school. So if I can skip this step, and you also have the best solution from last semester, and you can also ask me if you have questions. Right? So once you solve for alpha and beta, then you can invert to express x in terms of x bar. Why do you want to do this? Because you want to work with the new variable. You don't want to work with x. Okay. And so with the new variable, you replace x as a function of x bar. Okay, so x is now replaced by 1 over beta x bar minus alpha. Beta and alpha are some numbers, you know, that would give you that straight line. And therefore, the function f of x is now expressed as a function of x bar. So once you have this function in terms of x bar, you forget about the old function, work with this function, and use this function to do the projection. Okay, so that's really the key in this. Why? Could someone in the class tell me why you want to do the projection in the x bar space? Please do it quickly because we are doing a review here. So please participate, because that way that also helps you to remember rather than be a passive watcher. Yeah, right. Yeah, because you can take advantage of the Hilbert matrix, but in the exam, this is what you want to. You know, I hope that you are motivated to learn, not just because of the exam, but that's you know, to many that's the reality. So let's see. Yeah, so now you have. Let me make sure that I turn off. Yeah. So f is now expressed in terms of x bar, and that's 2 exponential of 1 over 4 beta, right? If let's see, let me double check to be sure. Yeah, I even have this over here. 1 over 4 beta x bar minus alpha. Okay. So projection in the x bar space means that you define a polynomial in terms of x bar, which can be written as C0 plus C1 x bar. You see, everything is in terms of x bar, not x. Okay, forget x now. and then plus C2 x bar 2. And the reason that I use the subscript 0, 1, 2 instead of 1, 2, 3 is because, you know, 1 is like x to the power 0, you know, so here you can write like this: C0 x bar to the power 0 plus C1 x bar to the power 1 plus C2 x bar to the power 2. You see, so there's a correspondence between the index of the coefficient and the power of the variable. Okay, that's a very nice way to remember. So now projection in x bar space means that you form the scalar product, right? Of this equation, right? P bar equal to f of x bar. Okay, so what it means is the following: you form the scalar product of 1 and p of x bar, and that should be equal to the scalar product of 1 and f of x bar. Okay. Now p of x bar and f of x bar are already defined there, right? So that gives you the first equation. The second equation is the scalar product between x bar. Okay, forget x now. We are projecting in the x bar space. So let me do this. It's even quicker. And all I need is just remove that. Oops. Okay. And the third equation would be the same, but now with the next basis function, right? The first basis function is 1, that's x to the power 0, x bar to the power 0. The second basis function is x bar to the power 1. And the third basis function is x bar to the power 2. And so therefore, all you need is 2 there. Okay, and let me move this out a little so that it's a little less confusing. That's it. From here, you should have 3 equations for 3 unknowns, and the 3 equations and 3 unknowns can be written as a Hilbert matrix, right, of order 3 times the column matrix of C0, C1, C2 equal to this, you know, the column matrix that contains all of these 3 numbers here. Okay, I can compact it, but I think you can see. Yeah, maybe let me leave like this. You can see the order. All right, and I should have the underbar here because that's the matrix. That's the 3 by 3 matrix. And so what are the coefficients of the Hilbert matrix? The coefficient of the Hilbert matrix would be as follows. For example, H11 is the integral of x bar to the power 0, x bar to the power 0, dx bar, right? And integrating from 0 to 1, meaning that x bar goes from 0 to x bar goes to 1, okay? So what is the coefficient? Let's say 1, 3. Here is how you keep in mind. 1 means the first basis function. 3 means the third basis function. What's the first basis function? 1. What's the third basis function? X bar squared. Right? So therefore, this coefficient H13 is the integral. Actually, I can do this. That would be fast. I can copy there. And all I need, so the first basis function is x bar to the power 0, and the third basis function is x bar to the power 2. Okay, that's it. Very, very systematic. In fact, if you know the C code, you can use the index of the matrix is going from 0 to 2 instead of from 1 to 3. That's a nice way to present also, because then you have a direct correspondence between the indices and the power. You know, that's nice. But it's okay to do like this. All right. So that would be the complete setup of the system, and I believe that your SAT calculator should be able to solve a 3x3 a system with 3 equations. Right now, if your calculator does not solve linear system, then you do the inverse ahead. The inverse of a Hilbert matrix is very nice. You can use Wolfram alpha to obtain the inverse and write it in your formula sheet. That's also very, very easy. But I believe that the most SAT calculator would solve the linear system for you. Okay. If anyone who have questions on this part, please ask me. Okay, do ask what I just said regarding writing down the inverse, okay, of the Hilbert matrix. I can demonstrate to you now, but it just takes more time. It's very easy. You can use Wolfram alpha and you get the exact solution. Okay, so what's the next question? So essentially, this is a review because I did go through this, and you also see in problem 5.1, right? So question 1 is done, set up the projection in back X bar space. That's question 2. And then the next is to solve the projection equation and give the expression for the parabola in X bar space. Okay. So I have already explained what it means, right, by parabola in meeting 36, I think, or 42. That's why you have the polynomial of order 2, right? That's basically the equation of a parabola. So.
Go back to the Hilbert matrix for a second.
Yeah.
Because you said it was a linear system. Are you just treating the x bar to 0, x bar to 1, and x bar squared as like individual variables, as opposed to being powers of one variable? Because if it does have that, it's also a linear system.
Oh, it's a linear system. Okay, so let me repeat the question. Anderson asked, he has a problem to see that this is a linear system, right, Anderson?
Yeah.
Right, that's the question. Well, okay, so let me write down. First, let me recall for you section 8C, okay? So essentially, it's very similar to what I wrote down here. Maybe let me look for something that is, so this Gram matrix here is the Hilbert matrix. Okay, so you see the matrix there, and Anderson asked, why is it a linear system? Okay, so it now, is the left-hand side clear or not? The left-hand side can be written as follows. Okay, so it's basically, a 3x3 matrix. Right, H11, H12, H13, H21, H22, H23, H31, H32, H33, and times this, right? That's the right hand side. Sorry, that's the left hand side. And you know the values of the Hilbert matrix, you can fill out the coefficient, right? 1, 1/2, 1/3. Right, that's the first row. Okay. Is it clear to you? That's the left hand side. Okay. How you compute the coefficients? That's what we did up here. Right? So h11 is the integral of 1 times 1. Let me use, x bar to the power 0 is 1. X bar to the power 01 is 1. And 1 times 1 is 1. So integral from 0 to 1 of 1 gives you 1. Okay? That's the first coefficient that is right here. And then you can do the same for the other coefficients, and you know how the Hilbert matrix look like. So that's the left-hand side. The right-hand side are just is just the column matrix of numbers, right? Because the integral of 1 times f of x bar. Let me take an example. Let me take this one. Okay, so that it's clear to everyone. Let me take the middle coefficient. The middle coefficient is essentially the integral, right, of x bar going from 0 to x bar equal to 1 of x bar times f of x bar. Okay, dx bar. And what is f of x bar? We already defined it up here. Right, so it's just a matter of copying this expression down here. Alright, and just put this integral here. Right, and the dx bar here. Alright, that's the, let me put a dot here so that you can distinguish that this is f of x bar. Right? So when you integrate this out, it's just a number. So the right hand side is just a column matrix with 3 numbers. Right? By the right hand side, I mean this one here. Right? So this right hand side here is a 3 by 1 matrix. Okay? So therefore clearly it's a system of simultaneous equation. It has 3 equations, and it's linear because the form of a matrix times these unknowns is linear. Okay. You have a question, Jackie?
We're supposed to use x bar in the Hilbert matrix or just x?
Can you speak louder?
We're supposed to use x bar or x.
I said x bar, right? You do projection in x bar. So you forget x completely. X is gone. You replace x by x bar. Why? Because we keep saying that over and over again. You want to work, instead of working on an interval from -2 to 4, because if you work on the interval from, maybe I should do this. If you do the projection on the interval from -2 to 4, you don't get the Hilbert matrix because the integral would be, maybe let me do like this. Okay, so this is projection in x bar space here. If you do projection in x space, then this is the formula. Okay, I need to write down so that you don't confuse this. Okay, projection. Perhaps better yet, let me. Okay, it's okay. Just because of time, I can rearrange this. So this is projection in x bar space. Okay. I just repeat the same equation. Now, if I do down here, projection in x space, then you would remove all the bars. Okay. This is the projection in x space. Maybe to avoid confusion, let me do this. Okay. Let me go back. and put bar on top of the C, so that the coefficient of the projection in X bar space would have the over bar, all right? And therefore, if I do that, then we go back all the way to the beginning, okay? And let me put the bar on the coefficient C. And therefore you have also the bar, the over bar here, okay? And likewise, you know, throughout, okay?
I'm just looking at some of the reports, they didn't use X bar in the Hilbert matrix. One you referred me to.
Please follow what I say.
Okay.
You know, if you look at the wrong report, that may be wrong. But if you look at Team 7, like I suggested,
I did.
it should be,
I'm looking at it right
you know,
now.
like this. Okay, so what's the difference between the two? The difference between the two is that when you form the scalar product, okay, so here let me go up here and copy so that I can do it faster. Yeah, so here, if you do this, form the three equations, okay, and if you do it in the X space, you remove the bar and you don't have the same equation, okay, of course. Otherwise, what's the reason of all this hoopla? I missed the okay. All right, so let me show you one example. Let's take this. So here, instead of the Hilbert matrix, okay, let me write like this. Okay, so you would have the following expression. Instead of the Hilbert matrix, you would have the Gram matrix. Okay, when you do projection in the X space, so I remove all the over bar. Here you don't have the Hilbert matrix, but you have the customary gamma. That's the Gram matrix. Okay, I remove all the bar here. And I think this is just from the expressions below. Okay. And again, I need this. Yeah, so this is the projection in the X space here. And what is gamma? What gamma? Let's give. Can someone? Let me test the class here. How do you write gamma 1, 1? What is gamma 1, 1? Remember gamma 1, 1 coming from forming the scalar product, right, of the equations, you know, of the polynomial in X there. So what would be gamma 1, 1? Okay, this polynomial here. Let me zoom out so that you have a big picture. Yeah. You see that polynomial C0, X0, C1, X1, C2, X2. Okay, you form the scalar product with that polynomial. So what would be gamma 1, 1? KZ?
It would be the integral from -2 to 4 of 1 times f of x dx.
Yeah, so like KZ said, that should be the integral from -2 x equal to -2 to x equal to +4 of 1 times x, and well, this is both 1, okay, because that should be x to the power 0. dx. Okay? But you see, this is not the same as H11. Okay? It's not a Hilbert matrix. All right? That's why you want to do projection in the X bar space. And once you obtain the coefficient C0 bar, C1 bar, C2 bar, right? Then you have P of X bar, and now you go back to X by replacing X bar as a function of X. And X bar as a function of X, you know already because that's where you started. Okay? X bar is a function of X. I didn't write it here, but I wrote it, should be in my notes. Section, this meeting here, right here. You see? When you find the equation for this straight line here, you know X bar as a function of X because you solve for alpha and beta. So in the end, to get the end result, you replace X bar as a function of X in this expression here. Let's see, right here. Okay. So let me do one more step so that maybe just this is enough. We add one page. Let me give you this and then okay. Now, so at this stage, you already know C bar 1, C bar 0, C bar 1, C bar, and C bar 2, okay? And so all you need to do is to replace X bar as a function of X, which you have derived, right? And that is X bar is equal to alpha X plus beta. And you know alpha and beta, okay? And it's the same thing here. The next term would be C bar 2 times X bar square, and X bar in terms of X is here. So therefore this, and just square it up. That's it. That's the result. Finish. 100 over 100.
Isn't that alpha plus beta X?
Yeah.
Yeah, let me take care of Jackie.
Would you just calculate the first two terms of the 3x3 Hilbert matrix in X bar? Because I'm getting totally different.
That's a Hilbert matrix. A Hilbert matrix is a Hilbert matrix. It's not the same as a graph matrix, right?
Well,
The first term is 1. The first coefficient H11 is...
of the Graham matrix.
Sorry?
Of the Graham matrix. The first term of the Graham matrix.
You want the graph matrix?
First term in numbers.
It's right here. Gamma 11 is the integral of x to the power 0. It's right here, Jackie.
Oh, I thought you said we were supposed to use X bar.
Look, I'm confused with your question, okay?
Okay, that is X and that.
Yeah, so forget the projection on X. I'm just explaining to you the difference between projection in the X space and projection in the X bar space.
Okay, do the projection in X bar, so that's what we're supposed to use, right? The X bar space.
We already did.
Yeah, number 4 in problem 1, you got to go back to X space.
Yeah, after you did the projection in the X bar space, this is the projection in the X bar space here, right? Okay. Can we close this?
Yes.
You have questions? Okay, no more questions.
That's fine.
You get the result C0 bar, C1 bar, C2 bar, you know, by solving this linear system that Anderson asked, okay, this one. So you get the unknown C0 bar, C1 bar, C2 bar. So the end result is right here, right, in terms of X bar. And now you want to express the result in terms of X. So all you need is just to replace X bar as a function of X. That's it.
In some way, I'm talking about the Hilbert matrix. I'm talking about projection.
I don't understand what you are asking, Jackie. We've already agreed on the Hilbert matrix, right? The Hilbert matrix is okay. Please manage time. Okay, if you'd like me to review more, I'll be happy. But you know, if we keep hashing over this, but I really like everyone to understand. This is the Hilbert matrix here. Okay. So if you integrate this from 0 to 1, then you can fill out this matrix, is it not? Is it a good or pick out a number, pick out a coefficient I can demonstrate to you. 1 is written down here.
Get the actual number.
It's 1.
Sorry?
1 is the actual number.
H11 is the integral of x bar 0. You know, this is the first coefficient in the Hilbert matrix here, right? And H11 is the integral from with x bar going from 0 to x bar equal to 1 of 1 times 1 dx bar. And that's equal to 1. Is it clear?
Okay.
This is very important, so make sure that. And then the result is that, you know, and I also give the example of H13 there. Make sure that you verify that. Okay. All right. So in a way, this is very important. So I really would like to entertain all questions possible. But let's see, I have maybe 10 minutes. I want to review problem 2, but please go ahead.
Do we have to solve the matrix or just write it down? I mean, it's very simple to write it out. Okay.
Yeah, you can write down the matrix and you can solve it, right?
So we don't have to actually solve it. We have to write down what it is for.
You mean to set up the matrix?
Yeah, instead of the matrix, we just write down that matrix.
Yeah, you can write down that matrix, but you want to explain how you get that matrix, right? And to explain how you get that matrix is very simple. You can just, you know, you can just explain like what I did there. Just 1 or 2 coefficients just to show that you understand. That's enough. Okay. And the expression for the Hilbert matrix is already there. And you just copy from your formula sheet, right? Okay. So can we close this problem, or is there any further question? Yes.
So Hilbert matrix is just going to make C's times those coefficients that C bar is used.
The Hilbert matrix? The
Like
Hilbert.
all the values of H1, H12, H13, those all end up being 1, right?
Yeah, this is the Hilbert matrix here. 1, 1/2, 1/3, so on and so forth. It comes from the integration up there.
Yeah.
Yes. So, you know, problem 5.1, solution guide, team 7. Okay. Okay, so let me mention a few words about problem 2. Problem 2, I indicated that you need to look at section 7, so please do so. So here I give you a double real root, right? So how do you, and so the first question is find the linear second order ODE in standard form. It's very simple. Let me write directly on the screen so it goes faster. Okay. So this would be lambda minus lambda 1, the characteristic equation, and lambda minus lambda 2. And in this case, lambda equal to lambda 1 equal to lambda 2. And so therefore you simply have lambda plus 1/2 squared. Okay. And when you expand out, you would have lambda square plus a lambda plus b, right, equal to 0. This is equal to 0. Where a and b are just the coefficients, right? When you expand out. And so this is the characteristic equation, and to change the characteristic equation into an ODE, you just replace lambda squared by y double prime, and lambda by y prime, and b or 1, b times 1 is b times y equal to, and in this case, you know, that's the left hand side, and the right hand side, there's an excitation here, so that's equal to g of t, okay, where g of t is the polynomial of second order. All right. So that's the first question here. The second question is the appropriate expression for the trial solution for the particular solution yp. You see that this is the second order polynomial. The trial solution has to include all of the order. So that means that yp as a function of t has to be, if you use d, you know, d is given, okay, like this. So you can use, say, c as unknown. So you have c0 plus c1 t plus c2 t squared. Okay, so this is the trial solution with 3 unknowns, right? 3 unknowns, c0, c1, c2. You need 3 equations. So you simply just differentiate this trial solution and replace into the left-hand side, where you need to do first derivative, second derivative, and replace on the left-hand side. And on the right-hand side, you have the polynomial, right? In terms of, you know, the coefficient for t0 is 0, the coefficient for t is 2, and the coefficient for t squared is 4. So you identify the coefficients of t0, t to the power 0, on the left-hand side, and the coefficient of t to the power 0 on the right-hand side, which is 0. You get the first equation. Then you identify the coefficient for t to the power 1 on the left-hand side with the coefficient for t to the power 1 on the right-hand side. That's 2. Get the second equation. And the third equation is the coefficient for t to the power 2 on the left-hand side with the coefficient for t to the power 2 on the right-hand side. That's 4. That's the third equation. 3 equations, 3 unknown. You can solve for c0, c1, c2. Right? So that's the how you get the particular solution, and that actually I just answered. There's 2 questions, in fact 3 questions here, because you can solve for the unknowns and you get the particular solution. The next question is the overall solution that you need to find a homogeneous solution. Okay? That's easier, and once you have the homogeneous solution, you can add to the particular solution. And remember, the homogeneous solution would have 2 unknowns, 2 parameters, because you need these 2 parameters to satisfy the initial conditions. Okay. But do not solve for the those 2 free parameters until after you add the particular solution to the homogeneous solution. Okay. And once you do that, then you get you obtain this the solution for this question. Okay, and the rest, you know, the last question, I have 2 minutes, I still have 2 minutes, so maybe I can cover that. Okay, consider a spring mass system. Let me zoom out a little here. Okay, so this is a question that was suggested back in probably fall 2013. You know, if you have a spring mass system, no damping, and with the mass and the spring constant K, right? And if you double the amplitude in the initial condition, meaning position and velocity, would the mass oscillate faster? i.e. the number of oscillations per second, or would the mass and